Hello chemistry people, Amy here. What I am doing for us today is a little video just running through the reactions of alcohols. So this is from 10.2 of the SL course. In a synchronous class, we discussed the reactions of the other functional groups. But for now, I'm just going to talk about reactions of alcohols. Before we get into this, I would suggest you have double check and make sure you remember how we name the alcohols, how we name the carboxylic acids, how we name the esters, and double check that you remember the difference between primary, secondary, and tertiary carbons. So I am just going to pause while I turn my computer around and then we can get started. Okay, so I've grabbed the parts of the 10.2 topic guide that relate to alcohols. I am not going to talk overly long about complete combustion. Most of my focus is going to be on oxidation and esterification. So let's very quickly talk about complete combustion. Basically, what it is your alcohol plus sufficient oxygen to be able to form carbon dioxide and water. It's exactly the same in structure as the combustion reactions that we see for our alkanes and alkenes. You've just got to remember the only tricky bit with the balancing. So let's work through an example. So let's look at C2H5OH, so methanol plus oxygen reacts to form CO2 and H2O. The only thing you need to make sure you're keeping in mind is this oxygen that's on the alcohol. I personally find it easier, instead of this sort of semi-structural, to change it to C2H6O plus oxygen makes CO2 and H2O. Just because if I've got the OH, I sometimes forget that last hydrogen, but that's a personal preference. So whenever you're balancing one of these, you go carbon, hydrogen, then oxygen. That is the easiest way to balance it. So I've got 2 carbons on the left, so I need 2 carbons on the right. 6 hydrogens on the left means a 3 there. Then I have 2 times 2 gives me 4 oxygens. 3 times that gives me 3 oxygens. So all up, that's 7. So sorry, that is 7O, not 70. I have 1 oxygen here, which means I need to get 6 here, which means I need to multiply by 3. Always double check your oxygens when you're balancing these, because the oxygens are what's going to get you. Okay, so that's all I'm going to talk about combustion with that example. I'd expect you to be able to write combustion reactions for any of those alcohols without too much bother. As long as you go carbon, then hydrogen, then oxygen, it should come out fine. So let's talk about oxidation. So technically, this is an oxidation reaction. I am adding oxygen onto that molecule. However, when we talk about oxidation, generally we are talking about the pathway alcohol to aldehyde to, depending on what type of carbon we're looking at, the carboxylic acid. Okay. So if we're looking at a primary alcohol, remember that means that my alcohol is at the end of my carbon chain, so my carbon is attached to at least 2 hydrogens. When I expose that to, let me just move this over a bit. When I expose that to heat, oh, no, I didn't mean to stretch. That'll do. So, yes. So when I expose that to an oxidant and I heat it, I end up with an aldehyde, which is, I don't know why I decided to write pi then. An aldehyde, which if I keep exposing it to oxygen, heat, and reflux, I end up with this fully oxidized carboxylic acid. In order for me to form an aldehyde or a carboxylic acid, it has to be this primary. My carbon has to be a terminal carbon. So when I say terminal, I mean at the end. So, for example, this is the process that happens with ethanol. So this is how we make red wine vinegar, white wine vinegar, apple cider vinegar. You're seeing the oxidation of that alcohol over time. So a reflux setup, let me just draw that quickly because it does come up. I have a heat source down the bottom, so that's my very crude drawing of a Bunsen burner. You then have your reaction vessel, and you then put a condensing tube into the top of it. So a condensing tube is basically a tube within a tube, and then you run water through it to cool down. So what happens is, as my reactants evaporate, the cold water condenses them into droplets and they fall back down. It basically enables you to heat something to just over its just over its boiling point, and then it falls back in. It's linked to, think about this in terms of bonding. This has H bonding and this has H bonding, whereas this is only dipole-dipole. If I just heated a mixture of those three things without the reflux mechanism, my aldehyde would just evaporate out because it's only held together with dipole-dipole. It's just held together with dipole-dipole, which means that it would just evaporate out. Now, the best oxidant for us to use is probably potassium dichromate. So potassium dichromate is one of the most powerful oxidants that we use regularly in the lab. So basically what's happening there is you start with acidified, so H+, and you've got the chromate in the 4 oxidation state. As it reacts, you then end up with the chromium in the 3 oxidation state. So generally, we would have acidified potassium dichromate, so H plus K2Cr2O7. Okay. sorry, I've got the wrong oxidation state here. My apologies. So this is dichromate 6. I got my Roman numerals around the incorrect way. So this is orange. And this guy is green because I'm obvious like that with my pen colors sometimes. Green. Okay. So when we're doing this reaction, this oxygen that I'm adding is coming from here. It's coming from this chromium. So this is the reaction that happens if I oxidize a primary alcohol. Let's look at what happens with a secondary. So carbon attached to 2 carbons. So that's where I've got a carbon in the middle with carbons on either side and a hydrogen. So these are just 2 different carbon chains, and I've got my alcohol in the middle. Again, when I react that with an oxidant and I heat and reflux, I end up with a, I'll call them C2 and C1 again. I end up with a ketone. So I go from a secondary alcohol to a ketone. And again, I use this same dichromate. So again, I will see this orange to green transition as my chromium acts. Now, this is now fully oxidized. I can't fit any more oxygens onto there. When I look at a tertiary, so that is where my carbon is attached to no hydrogens. So what I mean, I've got a carbon chain C1, a carbon chain C2, and a carbon chain C3. And I have my alcohol group attached there. It doesn't matter what I do. I can add an oxidant, I can add heat, I can add reflux. Nothing's going to work. I do not see a reaction. So my orange chromium that I added, I always write it around the wrong way. My orange chromium that I add here is still going to be here afterwards. Whereas my chromium will go green in primary alcohols and in secondary. In tertiary, there's nothing to be done. It doesn't react. Okay, so we've talked about, let's double check. Writing reactions for the oxidation of primary and secondary alcohols with acidified potassium dichromate. I'll talk about potassium manganate. So potassium manganate is actually this really beautiful purple color. It's this really intense, gorgeous purple. So this is KMNO4 by memory. Let me just double check. Sorry, let me pause. Okay, so I'm sorry about that. It is KMNO4, but I then got distracted trying to find you a picture of it. And for some reason, OneNote isn't letting me copy in from Google Images. So this MnO4 ion is purple. And when it is when it acts as an oxidant, it goes colourless. Now, by memory, that forms MnO42- as a product. So I've talked about reflux. Distillation is just heating up to a temperature between boiling points. So you can collect the evaporated, so you can collect one substance evaporated while leaving the other as liquid. Okay. Oh, I talked about it in the context of aldehydes and why we use reflux. So yes, I have talked about that. Let's talk about formation of esters. So for esters, and biology people and or people who are studying biochem as an option, this will be familiar to you. But in order to form an ester, I need one molecule with a hydroxyl on the end and one molecule with a carboxyl on the end. And I'm just going to do boxes to show the continuation of that, of those molecules. So it is a condensation reaction, so I will draw in blue. So a water molecule is generated, and what ends up happening, so what ends up being produced is a part of my chain from my alcohol, and sorry, my selectors don't seem to be working properly at the moment. And is my pen? Okay, now my pen decides to work, of course. So I end up making this thing with this COO in the middle and water. Because of the production of water, this is a condensation. And this bond here is called an ester bond or an ester linkage. This is also what we see between a glycerol molecule and fatty acids in a fat in biochem. It's also what we see for energy people when we are producing biofuels. This ester linkage is part of that. So this is the general reaction we see between an alcohol and a carboxylic acid. Let's do this with a specific alcohol and a specific carboxylic acid. So let's react ethanol, actually methanol, because I can't be bothered writing. So let's react methanol with ethanol. HOCOCH3. So we start by finding our water molecule, and it goes off to the side. Then what am I left with? I am left with CH3O. Then I go over to the other carbon, other molecule, CH3. So this is methanol ethanoic acid. So when we name this, we start with the name of our alcohol. Let me switch pen colors. We start with the name of our alcohol. So this was methanol. It's now methyl. And then ethanoic acid becomes ethanoate. So if I used propanol and methanoic acid, it would be propyl methanoate. This O8 is the ending that we give to compounds that have an ester. Okay. Okay, so thanks for that. That was our brief little explanation of the reactions of alcohols. Whenever you get asked a question about this on an exam, draw the molecule or double check if it is drawn for you so you know whether it is a primary, secondary, or tertiary alcohol. Make sure that you always include your oxidant. Make sure that you include your potassium manganate, Mn, which Mn is it? MnO4 minus, make sure you include that. Or make sure you include your potassium dichromate. Make sure you've got those reaction conditions, including reflux for those primary alcohols. Okay, thank you so much. Have a great rest of your day, and I'll see you next time. Bye.